Dear fellow attendees, my name is David Poirier-Quinot. I am a French VR/AR audio researcher, and it is today my privilege to present the results of my team's work on the improvement of binaural localization accuracy in VR games. This talk will focus on two questions. First, can players benefit from using individualized HRTF in VR? And second, how fast can one adapt to a new HRTF given a dedicated VR learning program? A word on me and my team for some context before I begin. I started as a PhD student working on the design of a radio direction finder for cell phones. A couple of constraints imposed on the system at the time led me to design a sound-based user interface that I developed as a virtual prototype in a simulated environment where I had a complete control over the propagation and the cell phone search conditions. Quite fascinated by the experience, I ended up working on acoustic simulation and audio perception in VR environments. From then on, my research focused on the creation of ecological and immersive auralizations in VR, the development and evaluation of audio rendering softwares, the design of web audio frameworks, libraries, and applications, and the design of VR games to support psychoacoustic studies. Following the short demo reel to give you an overview of some of my research projects.
Have you seen a light before? Have you knocked on my door? Have you only called my name until this time of shame?
My place now. Nothing special. My place now. Nothing special. You know, that feeling of
Pauvre malheureux! Si je passais par la casserole, qui te raccommoderait tes fonds de culotte? Ouais, pauvre malheureux! Si je passais par la casserole, qui te raccommoderait tes fonds de culotte?
Give you a more realistic response to your room. So we have the reverb option here that will simply add and add and add early reflections.
Binaural synthesis is a technique used in pretty much every VR/AR application. The technique is based on the application of spatial filters to an audio signal to reproduce 3D hearing over a pair of headphones. These spatial filters, or head-related transfer functions, reproduce the deformation, time, amplitude, frequency applied to any audio signal traveling from a given position in space to our ears. As such, HRTFs are, much like fingerprints, unique to each individual. The problem that concerns us here is that measuring HRTF on a per-user basis is not practical yet. It is a problem because our brain is so used to localize sound after, quote-unquote, filtering with our own HRTF in everyday life, that binaural synthesis using someone else's HRTF will almost certainly result in degraded localization accuracy. Said degradation often sees players searching for an audio source exactly where it is not, such as in front while it's behind them. which can be a deal breaker for designers who want to rely on binaural audio for more than, e.g., ambient sounds. Many methods have been proposed to improve binaural localization without access to personal HRTF. Some of these methods aim at adapting the HRTF to the user. The objective here is to select and/or modify an existing HRTF to get spatial filters that are perceptibly close to that of the user, i.e. resulting in not so degraded localization accuracy. Our first experiment will focus on whether using one of these methods can lead to improving one's performance in a VR game relying on audio localization. The second class of methods make use of the established plasticity of our brain to have users adapt to a new HRTF. The object of the second experiment will be to evaluate the performance, localization-wise, of a VR application designed for rapid HRTF learning. The HRTF selection method used in the first experiment had participants listening to two types of audio trajectories, illustrated on the right-hand figures. Each trajectory was spatialized using any one of 7 HRTFs available to choose from. Participants then ranked from best to worst, each HRTF based on how faithfully they reproduced the targeted trajectory for them. The ranking was repeated 3 times for each trajectory and was used to define an average best and average worst match HRTF for each participant. The VR game was designed to heavily rely on audio localization, serving as a best-case scenario to highlight a potential impact of HRTF quality on player performance. It is based on a first-person shooter, where players have to defend a position against waves of flying enemies attacking from every possible direction. It lasts 5 minutes, during which enemies will spawn increasingly faster and numerous, so that players are forced to use 360-degree audio localization, as opposed to 120-degree visual localization, to survive. 34 participants took part in the experiment. Each participant played 6 5-minute sessions distributed over 3 days. From one session to the next, participants alternated between best and worst match HRTF. This scheme, allowing for later intra-participant analysis, mimicked conditions where users have to use a different HRTF profile for different VR games. Following is a short video illustrating the VR game used in the first experiment.
New round. Get ready. +1.
The analysis of participant performance was based mainly on 3 metrics: in-game score, reaction time, and head angular motion. As could be expected, all 3 metrics indicated a clear game learning effect for all participants from session 1 to 6. A closer look at the results suggested that there was a slight benefit of best over worst match HRTF A for targets coming from above participants. So in the left hand figure, that's R6 spawn origin, which is highlighted in red. And B in the early stage of the game for one of the 2 groups, as illustrated in the right hand figure, reporting participant reaction time across groups and sessions. However close we looked, there appeared to be no overall long-term impact of the HRTF quality on players' performance though. As HRTF selection somewhat failed us, pending a second run of the experiment with a different selection method, we started investigating HRTF training solutions that would help players adapt to a given HRTF. We had two questions in mind. How fast can one learn to use a new HRTF given a dedicated VR game? And could room acoustic cues be used to accelerate the process? This second question arose while we were working on room localization, when we started wondering whether the addition of room acoustic to the anechoic binaural rendering commonly used in HRTF training programs would A. make the whole thing more realistic, i.e. believable, i.e. easier to accept as a new reality, because that is what HRTF training boils down to in the end, and B. provide users with more acoustic cues to help in the adjustment/learning process. For this experiment, we opted for a simplified version of the HRTF selection method, designed for fast and intuitive selection of a good, if not best, match HRTF from an existing dataset. Our intent here was to reduce the overall training duration, this selection method taking 4 minutes, where the previous one required 25, while still resulting in users starting training with a good match HRTF, as it has been shown to accelerate the learning process. The first version of the game was designed so that audiovisual feedback would progressively lead players to adapt to a new HRTF, but without them ever consciously participating in the learning process. It was eventually discarded during beta testings. The mechanics of the games requiring too much learning, plus we judged that it would not lead to as efficient a training as VR could offer. For the second version of the game, we decided to actually focus players on the HRTF learning itself. The main gameplay mechanic was based on a hide-and-seek game, the reward-punishment system directly tied to one's mastery of the HRTF. The game architecture was built around training sessions. For each session, players had 12 minutes to iterate through increasingly difficult training scenarios, each having them work on a specific known issue of binaural synthesis like up-down confusions or angular resolution. As a final touch, we added procedural scenario generation so that the game would lead players to train on those areas where they most needed training. For the experiment, the training was distributed over 3 sessions and 3 days. As can be seen in the top right chart, the first day started with an extra session for HRTF selection and baseline localization evaluation. Each training session for days 2, 3, and 4 was afterwards followed by a localization evaluation to assess players' performance evolution. Regarding the implementation, all the scene, creation, and audio rendering was performed in Unity, using the Anaglyph plugin for binaural spatialization and room acoustic rendering. Following are a couple of videos illustrating both versions of the training game. As the experiment is still ongoing, this is a preliminary peek into the results of one of our early participants. On the left hand, the 4 color maps illustrate the evolution of participant performance from session 0 to 3, from left to right and top to bottom. Each figure is a 2D unwrapped representation of performance on the sphere, where blue patches correspond to zones where a participant was consistently accurate in localization, and red patches zones where he or she was systematically mistaken. These color maps clearly suggest that this participant needed a little less than 2 sessions to adapt to a new HRTF. The right-hand figures also illustrate the evolution of this participant performance, focusing on a metric that highlights front-back and up-down confusions. The gray and red dots respectively represent correct and confused answers during the localization task, the latter decreasing from 47 to 12% between the first and the last session. To conclude, pending a better HRTF selection method, HRTF individualization doesn't seem to have much impact on VR player performance. And the proposed VR training program shows promising results, leading some participants to achieve near-perfect localization accuracy after less than 30 minutes of training. For those interested by a more in-depth look at these projects and others from my teams, feel free to browse through the websites in the resource section. Thanks a lot for your attention, and do not hesitate to reach out now or later if you've got any questions.